actual solution to the differential equation, or this initial value problem, and do a comparison. So the simplicity of having the iterates generated is what makes this thing reasonable and feasible. Internally, before Maple solves a differential equation, it runs through a checklist of an analysis of what the equation might be and what is an appropriate solution technique, and you can actually get some insight into what that process of identification and classification might be. So here's a differential equation. It can be classified with this task template, and here's the path to the task template. So again, we want to get this differential equation into the task template and hit the enter key, and you can see the command in this package called the eTools. But it's all set and ready to go. Just hit the enter key and Maple does its analysis, and it says it's a Bernoulli equation. Then you can actually tell Maple to give give back some of the information that it goes through internally as it attempts to solve this equation. So here's the dsolve command by setting the info level on dsolve to some number greater than 1, or is it greater than 0. So here is what Maple has gone through internally, and is being displayed for the user here, and it decides down here that these are not appropriate and that it's a Bernoulli equation. This ability to classify differential equation is actually in the context panel. So let's put the differential equation down here, and the context panel has the option classified as ODE, and it not only classifies, you can see it says Bernoulli, but it brings up the help page for how Maple tackles and what it does with the Bernoulli equation. Then getting to the heart of the material, here is the second order linear constant coefficient differential equation set up as with initial conditions, so it's an initial value problem. So this happens to model a driven damped oscillator, which is an important item in any course designed for science and engineering students. What does Maple have to say about such an equation? So here's the difference. The equation, here are the initial conditions. There is a tool called the ODE Analyzer Assistant. Now, where are the assistants? Under Tools, there is this classification of assistants. I think there's 16 or so. Maybe I haven't counted them recently. The Analyzer is an assistant, so it's called the ODE Analyzer Assistant. And some of these other ones in here are useful. One for curve fitting, the plot builder, which we just used. So these are useful tools. That's what we make use of. So it begins with the differential equation. So I'm going to just control drag that down here. And then in the context panel, you have the choice to solve the DE, which would give you the general solution with two arbitrary constants, or solve it interactively, and that's what I'm going to pick. I'm going to pick solve it interactively. It will launch the assistant with the differential equation embedded, and then I have the ability to insert these initial conditions. The initial conditions are inserted by interactively. Y at 0 is 2, and you click add, that puts it here. And this is a drop down, so y prime at 0, and I've chosen the value -1. Add, done. So now I have an initial value problem. I could have put simple boundary conditions in there too, but we're doing an initial value problem. So I can solve this problem numerically, but I can clearly solve it symbolically. And clicking that solve button will give me the analytic solution, and I can see it here in a bigger window. And so I have bypassed all of the rigmarole that it takes for solving, entering and solving a differential equation, and even graphing the solution. And the graph can be modified easily interactively. You make a copy, and you change the copy of y to y prime, for example. And now when you graph, you get a graph of y and y prime. In this instance, y prime would represent a velocity. And you could even do something like this. You change the horizontal axis, let it be y, and delete y from this collection of functions. Now when you could plot, what you're looking at is a trajectory in phase space. If you check this box, you see the commands that are being used: desolve to solve the equation, and a plot command to draw a graph. And then when you're done, you can return various things. You can return nothing, or the graph, or the solution, or you can see what the Maple commands are. So that ability to jump in and see what the differential equation looks like, what its solution looks like, how it behaves, etc., allows you to concentrate on the concept before you get into the nitty-gritty of the solution process and the commands and the steps that you have to take to solve the equation. So this is a look at what's involved really in solving this problem. I'm just going to execute these commands to save some time. Here's the differential equation. Here are the initial conditions. This is what the desolve command produced in the assistant. And this is the graph of the solution that we got for free in the assistant. So all of this stuff about how Maple returns the solution, it returns y of t equals, and then you have to grab the right hand side if you want to draw a graph. All of that is done in the assistant, making things much simpler. Now let's do stepwise. Let's see what Maple can do on a stepwise basis to help understand this process. So first of all, we want, I didn't want to do that. I wanted to hit this key. A fundamental set. Now, where did that come from? How do you get it? So you make the exponential guess, which you take and you put into the homogeneous equation, and you divide out the extraneous, or factor out the e to the lambda t, and you get the characteristic equation, which you then solve for the characteristic roots. And you put those back into this lambda over here, and you get e to this root and e to that root. So you're going to get these two solutions. But oh look, these two solutions have imaginary I in it, and they're not these two members of the fundamental set that Maple got. So how do you get from here to here? Well, you take, using the principle of superposition, you take linear combinations. Here you add and divide by 2, here you add and divide by 2i. So that's where Maple got its two members of the fundamental set. Next, you need a particular solution. So you can have Maple deliver you this particular solution, or you can use one of the two methods that you would see in a textbook. A variation of parameters or undetermined coefficients, and here I'm going to use undetermined coefficients. And the first thing you need is to get the correct template, which is suggested by the right-hand side, the driving term, and the characteristic roots. There's an interplay there. You take that, you find these two coefficients, a and b, by brute force. You put it into the differential equation, and you tell Maple, you figure out now what a and b have to be in order for this to be an identity. Well, there's a solve identity option in Maple, and it says, okay, if you let A and B be these numbers, there'll be an identity. The way I learned it many, many years ago, you collected like terms, and then you set each coefficient equal to 0. That would give you these two equations, which you would solve and get the same two values for A and B, which means that you now have a particular solution. That allows you to write a general solution, but that introduces these two new constants, capital A and capital B. And I think I will put that away so we have more real estate here. Now you want to evaluate A and B by use of the initial data, and this is just a way of getting the initial data into the appropriate equations without having to scroll up and down. Just the code goes up and grabs the right numbers, and you have to solve these two equations, which Maple does here. So that means that you can write this solution, but you aren't done until that solution matches what Maple delivered with its dsolve command. And so going through these steps, you realize a couple of things. First, there's a lot of steps, a lot of arithmetic, there's a lot of algebra. If you make a single arithmetic mistake, you end up solving the wrong problem. So you waste 45 minutes and you've solved the wrong problem, you got the wrong answer. Having Maple go through these steps prevents that. Also, it illustrates what the solution algorithm is, and if a student goes through a table like this a couple of times, can see how all these pieces fit together, it makes it much easier for the student then to learn the algorithm after they've understood why they're implementing the steps of that particular algorithm. In a course that includes first order linear systems, constant coefficients, here is an example of what Maple has to offer in that regard. So here is a pair of differential equations and some initial data, and the first solution that we'll come up with is with the analyzer assistant, which we've already used. The way you begin is you make a sequence of the two equations, and I'm using control drag to get them lined up. The context panel gives me the option solve interactively. And so interactively, I'm going to add conditions, and the conditions are x at 0, 3/10. Add that, and then this would be a drop down, so it's y at 0. And I pick 0, add that, click done. I now have a problem I can solve numerically, symbolically, and if I pick symbolically, I can see the solution in this larger window. And you see a linear combination of these two exponentials, 7t minus 9t, and a different linear combination of those same two exponentials. You want to draw a graph. This is a graph of x of t. The default domain here is 0 to 10, which is way too big because of that e to the 7t. So we can modify that by making, make this at most 1. And at the same time, we can add in y. So when we draw the graph, we'll get y at x and y both. And if we change the horizontal axis to be x and remove it from this list, when we click plot, we're going to get an orbit, trajectory, phase plane, and of course here are the Maple commands. So with this tool, you can get a solution, you can see some of the characteristics of what the solution looked like and how it would behave graphically. So it enables you, the instructor, to talk about the concept before having at their disposal a solution technique. Having obtained one orbit in phase plane, you might want a complete phase portrait. Well, here is a test template which will do that. let's set a window, -1 to 1, let's say, and -1 to 1. The equations here, 3x plus 12y, 4x minus 5y, and one critical point, 0, 0. Now, we're going to obtain trajectories, orbits, from various initial points, and we'll integrate in both directions, forward and backward, to get a complete orbit each time. So I'm going to integrate with a parameter running -3 to 3, and then I click Enter Data, and you can see I have a phase portrait, region. This is a direction field, so it shows me how the flow is going to go. The green dot is the equilibrium point. Then I click on a point, and a trajectory is drawn through that point. And each time I click, I get another trajectory, or orbit, and I can build up a phase portrait by clicking on enough initial points, and you can see I'm beginning to build a saddle. And so here's an easy way to get a phase portrait for an autonomous system. Having explored the differential equation system and drawn a phase portrait, now we want to get into some actual solution techniques. One is the use of the fundamental matrix. So we need the system matrix. So here in the matrix palette, we'll insert a 2x2 template, and then fill in the fields from the coefficients of the differential equations, 3 tab 12, and it's 4 tab -5. We want to give this thing a name, and we'll assign that the name A. And then down here, let's type the name A and hit the Enter key so we get an echo of that fundamental, of that system matrix. And then in the standard operations for matrices, we have the option matrix exponential, and here we put t, the variable is t, so we get e to the at. Now, this is not in its simplest form, with two-step simplifications of first we'll do an expand, and then we will do a combine. And that puts the fundamental matrix in its simplest form, and then I'm going to give it the name phi, a common name for fundamental matrix, PHI. Okay, now how do you use that? Well, phi times the initial vector is the solution vector. Okay, so phi, a period for non-commutative multiplication. The initial vector is 3/10 0, and I'll go control equal, which is evaluating in line, and this should be familiar. This is what the solution was. It had e to the -19, e to the 17, two different linear combinations, and we'll get a solution from the eigenpair approach, which is this standard approach taught in most differential equations textbooks, and we'll be able to compare that solution to this one. The second technique for getting a stepwise solution, first principles, is the method of eigenpairs, and that's what you typically see in textbooks. So we need to get eigenvalues, eigenvectors of the system matrix A. Well, that's already been defined, so let's type A and hit the Enter key. Then in eigenvalues, etc., we pick eigenvectors, and we get back a vector of eigenvalues in a matrix whose columns are the eigenvectors. So let's grab that matrix, which is the second member of that sequence, and then in select elements, we split into columns, so the two columns in this list are the eigenvectors. And I'm going to give this a name. I'll give it a name, capital X, so that x1 refers to this eigenvector and x2 refers to that eigenvector. So now we can form the general solution, which is shown here. A and B are arbitrary constants. A, space for multiply, exponential E, which I will get from my favorites palette. You can't just type E, you get it from one of the palettes here. I think I got it from common symbols. E, if you right click on it, you have the option to add to favorites, so that's how I populated my favorites palette. So there's the exponential E, and we want to raise that to the lambda 1t. Now lambda 1 is negative 9, so t, right arrow, space x1, so that's the first eigenvector, plus b space e to the 7t, right arrow, space x2. And let's call this general solution y. The capital Y. Okay, so we want to substitute t equals 0 into y in order to apply the initial conditions. So let's write t equals 0, hit the enter key, and use the substitute into option. We're substituting into y. So this is what the general solution becomes at t equals 0, and we would like this to become the vector of initial values, 3/10 and 0. So we want to reference this thing. So the simplest way to set up a reference is to give it a name like y0. Then down here, I will write that name, y0, and make a sequence of it with the initial vector, which is 3/10, 0. And these two vectors are juxtaposed, but I would like to set this first component equal to this first component, second component equal to the second component, which I can do with the equate command. You notice I now have two equations in which these components have been equated. So to solve that, I pick solve and take the simplest solve. And these are the values of A and B, which I would like to substitute back into Y. So let's do a substitute into Y. And here we have the solution generated by eigenpairs. I want to compare that to the solution we had in the fundamental matrix. So I'm going to copy this and paste it down here so it's easier to compare. And except for the way the fraction is written, 3 over 40, 3/40ths, you can see that these solutions are the same. There's another tool that's useful for solving nonlinear autonomous equations, and I'll use as an example the Lotka-Volterra predator-prey model. The tool is the tutor. Tools, tutors. Okay, there's 52 some odd tutors spread out over these subject areas, differential equations. There's this tutor. Now, I'm going to launch the tutor from this button, and I'm going to select the Lotka-Volterra model, select the plot. And so you can see here's the model. It's got some parameters, and you can modify those parameters in here. Initial values refer to the initial points on these two particular orbits that have been drawn, and this determines the size of the window. Now these orbits aren't closed because t didn't run enough or long enough. So we'll change that. And you can see that you can modify the number and kind of arrows. We'll try medium, see what that looks like. Okay. Now, if we go back and pick animate, then you can animate the drawing of the trajectory. From the initial points that you selected here. So it's a tool that will let you study autonomous but nonlinear systems without having to go through the hassle of figuring out how to code the command that does this. Now, this problem might be beyond the first course in differential equations, but it's certainly something that comes up in the applications. It's shown up in Maple Prime several times. And the interesting thing is that one can come up with a solution to this problem in a syntax-free manner. So we have a differential equation. It's a third order. So there are three conditions, and these are initial conditions, but this is a boundary condition. So this particular problem is like a post that was made to Maple Primes, and I tackled this in my advanced engineering math book, but here is the solution that was provided to this Primes post by a person named Maple Matt. And it was a coded solution, which has its place if you are doing this repeatedly and you want a procedure that does it. And you can see there's a bunch of Maple commands that one would have to sort out to figure out how to get this thing done. But I want to produce a solution that's done without having to worry about Maple commands. And the first thing I would like to do is to see the effect of changing the parameter p, right? Because there is a parameter p that controls the solution. So this slider varies p. The black solution is the perturbation solution. I think I took 3 terms. And the red solution is an exact solution if you can consider a numeric solution exact. Okay? So as p gets smaller, the two solutions approach each other. But they both move because they both depend on p. And as p gets larger, the solutions spread, and the region where the perturbation solution is a good approximation to the actual solution shrinks. So you can see the effect of p on the solution. Alright, but what is this syntax-free solution going to look like? Well, I left in place the computations to make this go a little bit more quickly. So here's the differential equation, and I've given it the name dE. This is the perturbation template. I used A, B, and C. If you paid attention up here, I believe the functions were called B with a subscript. Okay, I wanted to avoid that, so I called them A, B, and C because I was going to use the third order. And I gave that the name F. Okay, so you begin by writing y equals f, and then you invoke substitute into, and you substitute into the dE, and so this is what happens when you substitute this template into the dE. Then you want a series in the parameter p. And so you select series, and this dialog comes up. You are expanding about p equals 0. I'm going to take third order, and this checkbox means I don't get the order term O of p4. Okay, so here is the series in p. And what I want are the coefficients for each power of p. So this is the coefficient of p to the 0. This is the coefficient of p1. And this is the coefficient of p squared. And if I give this sequence the name q, I can reference this as q1, I can reference this as q2, and I can reference this as q3. Okay, so let's start with q1. That's the p to the 0 coefficient. So I write q1, so that's giving me the differential equation. Then I need to apply conditions to A, because that differential equation is in A. And that's where I include the non-homogeneous boundary condition. And I right-click and I just pick Solve the DE. And right-click is the old way of referencing the context menu, which is now a context panel. And so here is the solution, A of x, and I'm giving that, making that a function. So A of x is now a function. And I just do this 2 more times. So I have to write q2, and then the conditions on B, and I make that boundary condition homogeneous, use the context panel to solve the DE, gives me back the solution, and I make this a function by assign function. And I do that with q3, which is the coefficient of p squared. Again, the boundary condition on the right is homogeneous, and I get c of x. And all I have to do now is type f of x and control equal, and Maple will write out that approximation, A, B, C, as coefficients of p to 0, p squared, and that's what went behind this graph to produce the curve in black. And this visualization gives you a sense of what you've accomplished by this technique of forming a perturbation solution. This problem, number 10, is something that would probably show up in a second course in differential equation. It's not a trivial problem, a little bit deeper. I have a differential equation with this parameter lambda, making this an eigenvalue problem. Because this is of the form p of x, y prime, prime, this is a symmetric or formally self-adjoint differential equation. These separated boundary conditions, if joined to this differential equation, make this a self-adjoint problem. So we have a self-adjoint boundary value problem. We're looking for eigenvalues and eigenfunctions. What can Maple do for us here? You got to remember, Maple's dsolve command does not solve this problem. It will return zero solution because it cannot figure out a way to solve this problem. So here are some initial steps I want to take. I've got a couple of packages I want to load. Define the differential equation with a name, and enter the 2 boundary conditions with separate names. So I'm going to implement those commands. Then I want to execute this command, this enable typeset rule. Apply it to Bessel J and Bessel Y, because the general solution to this differential equation contains those functions. And rather than having the display as Bessel J, Bessel Y, I would like them to display as J sub 0, J sub 1, Y0, Y1. And this command will do it, but that Same thing can be done interactively, typesetting assistant. Now you can access the typesetting assistant from your typesetting rules under the menu, and the help page is here. This is what the dialogue is like. The way it works is in this drop down you find the function like Bessel J, select it. This checkbox tells Maple that upon input it should recognize J sub 0, J sub 1 as a Bessel function, Bessel J, and this checkbox says that on output it should be typeset, a Bessel J or Bessel Y, should be typeset as the single letter with a subscript. Okay, so I believe you get that done. We're clicking that, and now let's see a syntax-free solution. That's surprising that something as challenging as this problem can be done in a syntax-free manner. So I'm going to begin with a differential equation where I've made sure I've used the exponential e. Here is the differential equation. I'm going to have Maple give me the general solution, so solve the dE for y of x, and then I'm going to make y of x be this function, so sine function. Okay, now I want to apply the boundary conditions. So BC1, comma BC2, the boundary conditions. Not very pleasant looking things. Here's the end of the first equation, and here's the end of the second equation. These equations are homogeneous in C1 and C2. So for most values of lambda, C1 and C2 are going to be 0. I mean, that's the whole point of it, eigenvalue problem. So in order to get the values of lambda that give non-zero solutions to C1 and C2, I want to put these into matrix form. And I can do that with student linear algebra. Construction, generate matrix vector pair, where the unknowns are underscore C1, comma, underscore C2. So you get back a matrix, and a vector. The vector on the right-hand side is 0, and I want just this matrix, so select element number 1. So here's the matrix. Then I want its determinant, because this matrix has to be singular if C1 and C2 are not going to be 0 vector. So let's go down to student algebra, standard operation, determine. Okay, so set this equal to 0 and solve for lambda. Now, the simplest way to do that actually is to make use of the roots command in student calculus 1. What happened when I use solve, find roots, and I'm going to find all the roots between 0 and 100, and clearly I have to do this numerically. So Maple will now compute these 5 roots, put them in a list in ascending order. I like the roots command because I don't want to mess with fsolve, which will find the roots one at a time. You got to know where to start, etc., etc. So this Maple just did it for me. And I'm going to give this list a name. I'm going to give it the name capital lambda, L-A-M-B-A. Okay, so I've solved the first half of the problem, which is find eigenvalues. Now, surprisingly, it's a challenge to find the corresponding eigenfunction. What you would try to do is put the eigenvalue back into the problem and solve. But you will not get an eigenfunction. You'll get the 0 function, because this is only an approximation to the eigenvalue. If the eigenvalue was something like pi, then Maple's desolve command will be able to return you the eigenfunction. But because this is an approximation, it's not right dead on the eigenvalue, you only get the 0 solution. So here's a process that that I've devised to get an eigenfunction. I'll get the first one. The way I do it is take one of the equations. Because if you take both of the equations, that matrix will not be seen as singular because of the approximation. So I'm going to do BC1, and I'm going to put in that first eigenvalue. So I will evaluate at a point and make this be lambda 1. Notice that C1 is going to be a multiple of C2, and I can simplify the calculations by selecting C1, go up here to the pop-up, small pop-up, where it says isolate C1, and this is what I want to plug back into the solution. So let's do a substitute into, and let's substitute that into y of x. Well, we need to get lambda back in there, and you'll notice that you have a C2 that can be factored out, which tells you that the eigenfunction is determined to within an arbitrary multiple, which is always the case. So I'm going to evaluate at a point. I'm going to set C2 equal to 1. You can find some other normalizations scheme, L2 norm equals 1, whatever you like. I'm just going to set it equal to 1, and the eigenvalue is lambda 1. So here you have a representation, approximation to the eigenvalue corresponding to the eigenvector corresponding to the first eigenvalue. I'd like to draw a graph. So let's go to plots, plot builder. And let's tell Maple that in the plot builder we are going to graph. Well, the default plotting domain is -10 to 10. We really only want to be 0, 1, and I think the height looks best if we go 0 to about 8, and then tell me to draw that curve. There's a picture of the eigenfunction corresponding to the first eigenvalue. So a non-trivial problem solved essentially with point-and-click techniques that you can implement without having to first learn a whole bunch of Maple commands in order to make this thing work.
Okay, we're now going to start the question and answer period. In order to ask Robert questions, you'll need to open the Q&A window. It's at either at the top or bottom of your screen, depending on where you put your toolbar.
Okay, there is a question, and the question is, how are the subscripts being entered rapidly? So this is just a question about entering subscripts. So let's have a letter X, and we want to put a subscript. I use Shift minus, which lowers my cursor, and I put a 1. Now, there's an issue here. There really is an issue here. There's something to talk about here. That's something blocking my toolbar. I want to get at my toolbar. How do I get this black thing out of the way? I'll just move the screen. Okay. Tools. options. All right. This tools options dialog. I believe it's an interface. The underscore entry. You have to understand that there are two settings. And the default is this one. Inserts literal underscore, which represented a change along the way. I think it was maybe 16 or so where this change took place, and it drove me nuts. So I prefer the alternate setting, non-atomic subscript, because a literal underscore is an atomic subscript. It makes the variable an atomic variable. My preference is the going back to the original Maple, which is a non-atomic subscript. Okay, so that's my setting, non-atomic. This is a table entry. The table name is X. The 1 can be referenced programmatically. So if I have an X1, an X2, and X3, I can use the sequence command and say sequence X sub K, K running from 1 to whatever I want. You cannot do that with an atomic. So for me to make an atomic subscript, I have to type the X, put a subscript on it, then I select, and I use, I do it from the keyboard. I forget which one of these it is. Let me check. View? No. Edit. Maybe it's going to be edit. You know, I forget which one of these things it is here, but I select and I use Control-Shift-A. I don't know, Control-Shift-A, Control-Shift-A. That X1 is now atomic. And you will notice that for an atomic, the subscript is in italic, whereas for a table entry, the subscript is not italic. And if you want to see where the atomic variables are in your document, if you go to View and you select Atomic Variables, you'll see that they show up in maroon, or whatever that color is. When they're in that red color, the subscripts are not italic. If you take away the indication that you have atomic variables, then the subscript becomes italic. So depending on how you set your subscripts to work, you will use the keyboard. My use of the keyboard is Shift and the minus sign. I believe for those with the alternate setting, it's Shift and 2 minus signs. But I'm not sure, because my fingers are trained to do it the old way, and my brain being 77 years old just refuses to adapt to this default setting, which I really don't like. So I hope that answered your question. If not, here's my email address, and you can email me, and we can have a further conversation about this by email. So it's rlopez@maplesoft.com. And if you want a copy of these worksheets, you can also contact me at that address and ask for the worksheets, and I'll be happy to probably have to send you a download link, because there's a bulky bunch of these, and a lot of mailers don't like big bulky attachments. So I send a download link from which you can grab up the files. There are no other questions here. So the clock says 3 o'clock. I think it's time to go.
Well, it looks like that's all we have for today. If you have any additional questions about today's webinar, please feel free to email them to webinars@maplesoft.com. Thank you for joining us for today's webinar. We hope to see you again soon.